Good evening to all of you. Welcome to Wallah. So in the last class we have discussed on chlorination topic. So if anyone having any doubt from the previous class they can ask. Today's topic is softening, which is a part of basically a water treatment. So before starting the softening process, let me give you a small intro. Before softening, what are the things which is there? Generally, few treatments we put it as a miscellaneous treatment, the treatment which we are not doing regularly for the surface water treatment. Softening is one of them. The reason is, generally in the groundwater treatment you will find the hardness is something which we want to remove it mostly, and for that reason we need softening for that. Now, softening is a process which is something which is required for the groundwater treatment, because generally in groundwater as a source, if you are taking it, generally hardness of the water will be very high, and in that case you need to go for removal of those hardness. Now, while removing the hardness, some basic things which you need to know. The first thing, it is about the hardness itself. Hardness is something which occur due to the multivalent cation, or multivalent cation is having a capacity to produce hardness. Either it will react with some carbonates or bicarbonates. So if it reacts with carbonates, in that case it will form carbonate hardness. That is something what you are calling it as temporary hardness. If it is reacting with the non-carbonates thing like chloride, SO4 minus, that means sulfates, nitrite, if it is reacting with this, in that case, that is what we are calling it as non-carbonate hardness, or we are calling with another name which is permanent hardness. I think that part is clear to you. Just wait for 1 second. Okay. Now, we have multiple methods to remove this hardness. Especially for the temporary hardness, we have different methods. Then for permanent hardness, again, we have many methods. Right now, the method which we are going to see will be the softening method. In that softening, definitely our target will be both non-carbonate hardness and carbonate hardness. Now, see here. In the water softening process, the process is basically removal of hardness. First, if you want to remove the temporary hardness, what you will do generally? For the temporary hardness removal, let's say if the water is having calcium bicarbonates, you will heat that water. After heating, the calcium bicarbonate will be converted into carbonates in a form of precipitates. It will get settled down. Now the thing is that with a calcium bicarbonate, by heating you can do, but if you want to remove the temporary hardness for magnesium, you need hydrated lime for this. That means lime will be required for the magnesium carbonate part to convert this into something which we can settle it down, which is an undissolved form, MgOH twice, which is settleable. Then for Mg bicarbonate, again you need lime only. It will be converted into calcium bicarbonate. Now calcium bicarbonate is again something which is soluble. So again you need to provide 1 mole of calcium. This is something what we are calling it as slacked lime, hydrated lime, no? CaOH twice. Calcium bicarbonate plus CaOH twice, it will again react, and in that case it will form calcium carbonate. See, calcium carbonate, why in every reaction we are coming for either calcium carbonate or MgOH whole twice? Because these are actually present in the water in undissolved form. So these are not in dissolved form. So in that case, this will be settled down by precipitation or by sedimentation. Now here, as you have seen, that for magnesium carbonate, you need only 1 mole of hydrated lime. Like 1 mole of magnesium carbonate needs 1 mole of lime. But magnesium bicarbonates need 2 mole of hydrated lime. Now this something which as a note I have given to you, you all have to remember. See, these reactions are important for you. Even for the numerical question, these reactions are important. Without reaction, you will not be able to solve any questions. Now if you talk about the lime process, in a lime soda process, the first one is the lime process. Just now you have seen the effect of lime here. With a simple lime process, what you have done it, the calcium bicarbonates gets converted into calcium carbonate, magnesium bicarbonates get converted into calcium bicarbonate, and then this calcium bicarbonate will be again react with COH whole twice to form calcium carbonate. Magnesium carbonates will react with hydrated lime to form MgOH whole twice, which is again a precipitates for you. For a precipitates, I have shown a downward arrow. Okay, just to let you know that this is the precipitates which is going to be removed. So with the lime, you can see we are easily removing all type of temporary hardness. All type of hardness, which is the carbonate hardness which we are talking about. So all the temporary hardness will be removed with the help of lime. Now comes the soda. Now comes the second part, which is the soda. Soda means soda ash, which is Na2CO3, Now this is something which is required for the permanent hardness removal. If there is a hardness which is formed, because of magnesium reacting with either chloride SO4 2- NO3-, if this is nothing but this is something what we are calling it as magnesium chloride or magnesium sulfate, this is basically nothing but the permanent hardness of magnesium. If it reacts with lime first, it will form MgOH whole twice. So this is something which we can precipitate it out. This is again Ca2 plus reacting with chloride SO4 2-, or at a time only one will be there, not all three. So basically in this reaction, what you have done it, you wanted to remove this magnesium non-carbonate hardness, but it actually gets converted into calcium non-carbonate hardness. Now the problem is not solved. Our intention is to completely remove the magnesium non-carbonate hardness. Now this is converted into calcium non-carbonate hardness. Now this calcium non-carbonate hardness will react with soda ash, which is Na2CO3, and it will form CaCO3, which is again a precipitates for you. CaCO3 again a precipitates for you. CaCO3, which is again a precipitate for you, that you can remove it out. That means what we have understood with this reaction, that magnesium non-carbonate hardness, to remove, or you can write like this, to remove magnesium non-carbonate hardness, you need both lime and soda. But to remove calcium non-carbonate hardness or permanent hardness of calcium, you need only soda, Na2CO3. Is that clear to all of you? Now, what happens even if in your water some amount of carbon dioxide is there? So if you are adding some amount of hydrated lime, so that hydrated lime amount is some amount of hydrated lime which you have added, that will react with the CO2 also. It will form calcium carbonate. So you have to always check whether how much carbon dioxide content is there in the water. If it is very high, then you have to add the, if it is very high, in that case you have to remove it first. If it is manageable, in that case you add some extra dose to take care of carbon dioxide also. So this is about the lime soda process. With only lime, you can remove the temporary hardness, but if lime and soda is combined, like if you are using lime and soda both, that is what we are calling it as a lime soda process. You can remove temporary hardness as well as permanent hardness both comfortably. Is that clear to all of you? Is that clear to all of you, my dear? Is that clear to all of you? Okay. Now see some silent feature of lime soda process. The first thing, the lime soda process reduces the corrosion of pipe because you are adding lime. Definitely what happens due to increased alkalinity. It also helps in killing bacteria because of high causticity. One of the method of disinfection, yesterday also I told you, it is the excess lime treatment. If you go beyond 9.5 pH, in that case you will see most of the microorganisms are dead if you are going above 9.5 pH. It also helps in removing small quantities of Fe and Mn, but the process produces huge quantity of sludge because Fe and Mn is going to be creating more amount of sludge for that. Complete removal of hardness cannot be accomplished by the chemical precipitation under normal condition in the treatment plant. This is the one of the issue with lime soda process. That in a lime soda process, ultimately, after converting into the carbonates in a precipitates format, you want to remove it. But you also know that precipitates are not able to settle completely 100% in the tank. Some part will be remain there in the water itself. Now hardness in a dissolved format up to a limit it's allowed. You know the hardness drinking water standard is 200 milligram per liter, permissible limit or acceptable limit, and the rejection limit is 600 milligram per liter. Now, so up to 200 milligram per liter it is allowed in the drinking water, na? But in a dissolved format, not in a non-dissolved format. Because in non-dissolved format, it will be easily seen by the person. In that case, nobody will drink that water and it will be difficult for us to drink also. So what we do generally, if some amount of hardness which is present in a carbonate format and you want to remove it, instead of removing it, we actually put some recarbonation technique so that we actually convert that into from carbonates to bicarbonate, from calcium carbonate to calcium bicarbonates. Calcium bicarbonate is in basically it's a form of it is dissolved form. It is in dissolved form. Calcium carbonate is in precipitates form. So basically from non-dissolved format to dissolved format you have converted it. So that's what we do. Lime remove entire carbonate hardness that you have already seen in the chemical reactions. Lime reacts with non-carbonate hardness of magnesium to convert into non-carbonate hardness of calcium. All these things you have already seen. Even regarding the CO2, that also we have discussed. So here they have mentioned it. Thus, if the concentration is more than, CO2 concentration is more than 10 milligram per liter, we remove CO2 first by aeration before adding the lime. So if concentration of CO2, it is more than 10 milligram per liter, in that case, first you remove the carbon dioxide. Otherwise, what will happen? Whatever the CaOH you are adding it will get react with CO2 first. In that case, the amount of CO2, CaOH which you have added, the amount of lime which you have added, will not be utilized uh, in a fully best way. Okay. Now, in the lime soda process, a complete flow chart I am giving to you. So here you are doing the mixing of lime, soda ash, and alum. Here you are mixing it. Then the flocculation comes. You give some time for the floc formation, and then comes the sedimentation. Because you have added some lime also, no? So definitely you have to give some time for the floc formation, and this is the sedimentation tank now. Here in the sedimentation tank, your calcium carbonate, your MgOH twice, all the precipitates part, your AlOH thrice, all these things which is basically precipitates will get removed from here, and the water, the supernatant part will go into the recarbonation unit. In the recarbonation unit, as I said, again the carbon dioxide is added here. Basically, you want to convert all the non-dissolved or all the carbonates which calcium carbonates which are remain in the precipitates format, that you want to convert into the calcium bicarbonate part. Now after that it will go into the rapid sand filter, and then you can get the softened water. This is the complete lime soda process which I gave it to you. Is that clear? Is that clear to all of you, my dear? Any doubt in this? Okay. Now, some other property of lime soda process. When lime soda is added with alum, that's something which you have seen. When that means the softening and the coagulation, you are doing it together. Process is combined, the lesser quantity of coagulant is required. Now this is again a very good property, that if you combine softening and coagulation together, you need lesser amount of coagulant dose. Lime soda process reduces the corrosion of pipe due to increased alkalinity. This is something we have already discussed. This part we have already discussed, so no need to repeat it again. Now comes the next process, which is ion exchange process. Ion exchange process. We also call this as cation exchange process. In this process, what we are doing it, we pass the influent, the water sample or the water through a zeolite bed, and then at the bottom it is going to be collected after passing through the zeolite bed. Now in this zeolite bed, how the reaction take place, that we need to understand first. So let me show you the zeolite bed first. This is the zeolite bed reaction, chemical formula I will say. Na2O, Al2O3, SiO3. In a single word we are calling it as a green sand, but it is basically alumina, sodium, alumina and the silica. Sodium, alumina and the silica. Now, this is something what we are calling it as zeolite. So zeolite is a natural or synthetic cation or base exchange hydrated silicates of sodium and aluminium, and it is something which we are also calling it as a green sand. Now what it does actually, when the water passes through them, so in a short format I am writing this as Na2Z, Na2Z in a short. Z means the remaining thing. Now, if the water passes through this zeolite bed, water is having either calcium or magnesium carbonate hardness or bicarbonate hardness or non-carbonate hardness. So all type of hardness it can be there with the related to the calcium and magnesium. Now if it reacts, what happens? They change their cation. Now Na will go with this one and C and Mg will go with Z. So calcium and magnesium is something which is retained in the zeolite bed. This calcium and magnesium cations are retained in the zeolite bed, and the water which is passing as a effluent will have only this. Now first thing, You know the water is having hardness not because of the anions, because of the cations. The cation is having the capacity to produce hardness. So if you are able to capture, if you are able to remove the cation, which is calcium and magnesium, multivalent cation which we are talking about, if you are able to remove, that is something which is attached, or I will say removed by the zeolite bed. If you are able to remove that, in that case, the water will not have any hardness. And the hardness which and even this Na plus, sorry, NaCl or NaSO4 2 minus or NaSCO3, like that compound can be formed. This Na is not having a capacity to produce hardness. So even though Na is having carbonates, bicarbonates, non-carbonate hardness, anions, all these HSCO3, SO4 2 minus, Cl minus, CO3 2 minus, whatever type of hardness you have, whatever type of anion you have, but this anion cannot produce hardness with the help of Na plus or with Na plus, because Na plus is monovalent cation, and monovalent cation cannot produce hardness. Is that clear? So this thing, if it is goes with the water, we don't have any problem. We don't have any problem with that. And that's what happens in the zeolite bed process. That's what happened in the ion exchange process. And the good thing is what? After some time, when you feel that now the bed is completely saturated with the Ca and magnesium cations, and you want to regenerate the bed, what you simply do with this bed, Ca and Mg, the bed which needs the regeneration, we put that bed, that zeolite bed, into a brine solution. Brine solution is having 5 to 10% of, or 5 to 10% solution of salt. So in that case, it is something what we are calling it as a brine solution. If you dip into that, what happens? Again, the NaCl, which is there in the brine solution, this Na will go with the Z, and C and Mg will go with the chlorine. So it will again form Na2Z, which is the original zeolite bed, and then Ca and Mg will react with Cl2. Either CaCl2 will be there or MgCl2 will be there. So that's something which is nothing but a permanent hardness which will be formed. So during regeneration, some amount of permanent hardness will be formed, but that is something, the amount is very less. This amount is very less, so you can manage with that. But good thing is that the same zeolite bed is now regenerated, ready for use again. This Na2Z, which is the zeolite bed, this is again regenerated for next use or next application. Now, good thing about the ion exchange process, it completely removes the hardness. It does not discriminate between temporary hardness or permanent hardness. Any type of hardness will be removed by this ion exchange process. Any type of hardness. And the another good thing is that during the process, just like unlike lime soda process, here no sludge will be formed. No sludge will be formed here. There will be no chance of sludge formation. Even the zeolite bed, which I told you, you can regenerate that bed with the help of brine solution. Okay. No problem of incrustation of pipe as in the lime soda process, but it is not suitable for turbid water. There is some issue also. This ion exchange process, you cannot pass turbid water through the zeolite bed. That is an issue. You cannot pass turbid water. The water is having with turbidity. That type of water you cannot pass through zeolite bed. It also leaves NaSCO3 in the water, which causes foaming in the boiler feed. All these things you need to understand. Now, this process is costlier for the water containing iron and manganese, because if you want to remove iron and manganese, because Fe and Mn zeolites are formed which are or which cannot be regenerated. So because if you want to remove Fe and Mn, in that case what happens, the Fe and Mn zeolites will be formed, and that's something you cannot regenerate with the or regenerate into sodium zeolite again. Thus zeolite is wasted if Fe and Mn are present. So you have to take care of that in the water sample Fe and Mn will not be present, because if Fe and Mn will be present, in that case you cannot regenerate that with the brine solution. That's the thing regarding the ion exchange process. So I hope it is clear to all of you. I hope this method is clear to all of you. I hope this method is clear to all of you. Any doubt or any query? Okay. Now, if you want to find out the volume of ion exchanger, you can simply have the total hardness value divided by the capacity of ion exchanger. Simply divide the value, you will get the volume. This value will be generally in kg per day, and this value will be generally in a kg per day per meter cube. So if you divide this, you will get the volume of ion exchanger. So regarding the permanent hardness removal, generally three methods we suggest. One is the lime soda process, another is the ion exchange process, and the third one is the demineralization process. Lime soda process is something which we have discussed already. Ion exchange process also we have discussed just now. Demineralization is basically either with the help of reverse osmosis or something else, either with the reverse osmosis or electrolysis. So that is a different thing. Now we'll go for the problem part. Now we'll go for the problem discussion. So first problem to all of you. The first problem itself, I have taken the bigger one so that you will have a complete idea about what we have discussed in the last 30 minutes. Okay. Now see what they're asking. I hope you already, once you have read this, once you have completed the reading for this question. Calculate the annual cost of slag lime and the soda for treating 70,000 liters of water. So they have given you the discharge if the water contains the following impurities. Calcium carbonate, that means it is existing in a form of calcium bicarbonate, 280 ppm. NaCl is given as 35 ppm. MgCl2 is given as 138 ppm. Fe2O3 is given as 55 ppm. MgSCO3 twice is given as 100 ppm. CaSO4 is given as 110 ppm. MgSO4 is given as 80 ppm. And SiO2 is given as 40 ppm. That is what which is given to you. Now purity of slag lime is 85% and that of soda is 100%. That is what which is given to you. The slag lime cost is 80 rupees per quintal and the soda for 400 rupees per quintal. This is what you are having. This is what you are having. Okay. See here. First we'll calculate the lime part and then we'll go for the soda part. So in the lime calculation, if you see, first one will be this calcium bicarbonate, which is 280 ppm. Calcium bicarbonates, it needs lime to get converted into calcium carbonate part. So calcium bicarbonate, if you know the reaction, how much it is there? 1 mole of calcium bicarbonate, it needs 1 mole of slag lime, which is CaOH whole twice. So 1 mole of here it is given as CaCO3 require as SCO3 require 280 require 1 mole of CaOH whole twice. So 1 mole of calcium carbonate is 100 gram. So 100 gram of CaCO3 require, this is how much you will, can you calculate this for me? CaOH whole twice, how much you are getting for this? Around 74 gram. The molecular mass of calcium hydroxide is nothing but 74 gram. Oxygen 16 plus 1, 17 into 2, and then 74 gram. Okay. Now, 280 gram of, currently we have 280 gram of CaCO3, that will require 74 divided by 100 into 280, how much it will be? That much gram of CaOH whole twice. How much you will get it for this? According to my calculation, I'm getting around 207.2 ppm. 207.2 ppm of CaOH whole twice. That much will be required. Now this is for the one. You know, lime is something which is used for others also. NaCl will not require lime. MgCl2, magnesium non-carbonate hardness. This is something which is, this needs lime. So again, 1 mole of, or directly you can write MgCl2, 1 mole of MgCl2 require 1 mole of this something. How I'm able to write this? Based on the reactions which I told you in the starting of the class. Okay. So 1 mole of MgCl2 require 1 mole of CaOH whole twice. Now 1 mole of MgCl2, how much will be the molecular mass? Can you calculate? Roughly, chlorine will be 35.5. So 35.5 into 2, 71 plus. So approximately 95 I am getting it. So 95. Directly I am writing it for you. So 138 ppm of MgCl2 will require, this will be 74 divided by 95 into 138. How much you will get it? I am hoping that all of you are solving with me. Prerna is asking, sir, I am preparing for GATE ES 2026 Environment Science. Can you please start a crash course for it, please? Crash course is something which we are gonna start on maybe October or last of October. Either in starting of October or maybe in the last of October. So every day we go for that. Like that, we'll go for this year also for GATE 2027. One not 7.49 ppm. 107.49 ppm. 107.49 ppm. One not 7.49 ppm. Is that clear? Come to the third one. Come to the third point. Now, for MgSCO3, magnesium bicarbonates, 100 ppm is there. So magnesium bicarbonates, they need 2 mole of, so 1 mole of MgSCO3 twice require 2 mole of CH whole twice. Am I right or wrong? Okay. So if you calculate the molecular mass here, how much it will be? Around 146 we are getting for this. So 146 gram of MgSCO3 twice require 2 mole, that means 74 into 2 gram of CaOH whole twice. Currently, how much MgSCO3 is given to you? 100 ppm. So 100 ppm of MgSCO3 twice will require, so 74 into 2 divided by 146 into 100. how much you are getting for this? This much ppm. Clear? Now the fourth one is MgSO4. MgSO4 also require, and even for CSO4. CSO4, no, CSO4 does not require lime, but MgSO4 will require definitely. So 1 mole of MgSO4 require 1 mole of CaOH whole twice. So MgSO4, how much it will be? Around 120. So 120 gram of MgSO4 require 74 gram of CaOH whole twice. Currently they have given 80 ppm of MgSO4. So 80 ppm of MgSO4 will require 74 divided by 120 into 80. How much it will be? $49.34 ppm. 49.34 ppm. So if you add all these, you will get the total lime required. You will get the total lime required. So you have first here 207.2 plus 107.49, 101.3698, 49.34, 49.34, bracket closed. So total I am getting 465.3998 ppm. This much what we are getting. Now they have already given you the discharge, which is 70,000 liters per day. So Q is 70,000 liter per day. I can convert this into 0.07 mld. Total lime required it will be Q into concentration of lime required 0.07 into kg per day. This much you have. But the thing is that they have given you something, the slag lime is having only 85% purity, and they want you to calculate for the annual. Okay, so annual means total lime required annually if you want to find it out. So you have to multiply this with 365 also. So after multiplying this with 365, it will be 11,890.605 kg. They have given you the value also, like slag lime is costing 80 rupees per quintal. So if you want to find out cost also, cost of slag lime, so it will be 80 rupees is the cost for per quintal. You got 11,890.605. That is the actual amount you need. But you know it is having only 85% purity, so you have to take something extra. You have to compensate with this. So that's why I'm dividing this by 0.85. Now this value is in kg. You need to divide this by 1000 to convert this into quintal. How much you guys are getting it? After completely solving this, we are getting around 1. Now the next one is the calculation of soda ash. Calculation of soda ash. Soda ash will be required in, it will be required for MgSO4, it will be required for CaSO4, it will be required for MgCl2. Am I right? Only for these three. Only for these three. And what is the soda ash molecular mass? Now some values. Now this time I am directly calculating the soda ash concentration required. First of all, for MgCl2, the molecular mass is 138 now. So 106 is the molecular mass of soda ash divided by 138. Currently, how much soda ash you are having? Sorry, MgCl2 is 138 ppm, na? But what is the molecular mass of 138? Achha, it is only 95. Sorry. Plus, again, 1 mole of soda ash, so 106. Next, which one we are taking it? After MgCl2, MgSCO3. No, MgSCO3 will not require. CaSO4. CaSO4, how much will be the molecular mass? 40 plus 32 plus 64. 136. Into, currently how much they are available? 110. 110 ppm. Plus again the next one, 106. For MgSO4 also 1 mole of soda ash is required, and MgSO4 molecular mass is how much? I think that is something which we have already calculated. It is 120 into 80. Sum it up. How much you guys are getting it? According to my calculation, I am getting around 310.36. That much soda ash concentration required. Now this time I'm directly finding the cost of slag lime. So annual cost of slag lime, if you calculate, first you need the concentration, which is 310.36. Then you need discharge, but in MLD, so I'm multiplying that. See, in the first step I have done all the step which is required, like whatever step is required, each and every step I have shown it to you. Now in the second calculation, this one, for the soda ash calculation, I'm going in with the short format, so that you can use this type of calculation for the competitive exam like GATE and all. So concentration, then discharge, into the purity level is completely 100%, but we need to convert this into quintal. So that's why I'm dividing by 1 by 100. Now 365 because the values I want in, which is the annual cost of slag lime, which is the annual cost of slag lime, and what is the cost of per quintal for the slag lime? It is 400 rupees. 400 rupees. Check whether all the data I have taken or not. Check whether all the data I have taken or not. So around, after solving this, 31718 31718.792, this is what I am getting. 31718.792 rupees. Okay. Now you all have understood this in a complete clear manner. Any doubt with this question? Any doubt with this question? Now, if this question is clear to all of you, the two method which we have discussed just now, I have given a rough comparison to both the methods. Let us just read this once. Comparison of lime soda and zeolite process of softening. In terms of size of plant, lime soda will have bulky and the large, like definitely a large unit. Zeolite process, it is very a compact process, so in that case compact design will be required. Skilled supervision, careful and skilled supervision is necessary for obtaining results. This is completely automatic process, so easy to maintain. Sludge troubles, definitely in the lime soda process, large amount of sludge comes out, and that is something which you have to dispose it. Zeolite process, no sludge comes out, so in that case, it is not a problem for you. Post treatment if needed, yes. In this, recarbonation is needed. Recarbonation is must after sedimentation and filtration. If recarbonation is not done, incrustation of pipe walls of distribution system may occur, which is something dangerous for us. And dangerous in terms of water supply. No such post treatment is required because whole, complete, zero hardness free water you will get it. Result obtained. This can be produced water of hardness not less than about 50 milligram per liter, therefore useful for public supplies only. But this type of ion exchange process, you can use it for industrial supplies also, like for boiler and all, you can use this ion exchange process. Removal of color due to iron and manganese. This lime soda process can remove the color due to iron and manganese, but only to a very small extent. But in a zeolite process, it can remove the color due to iron and manganese, although very costly for treating such water because the exhausted Mn and iron zeolites cannot be regenerated. So color you can remove it due to iron and manganese, but the issue is iron and manganese retained zeolite, you cannot regenerate it. So it will be wastage for you. Effect on bacteria. The increased causticity may help in killing the bacteria, pathogenic bacteria, especially when the alkalinity caused by the calcium and magnesium or sodium hydroxide of 20 to 50 milligram per liter is maintained for 4 to 5 hours. No such advantage is offered by the process. Regarding this, no such advantage you will find in the zeolite process. pH of the treated water increases the pH of the water, which reduces the corrosion of the distribution pipe. pH of water, we are not touching it here. The pH of the water is totally not affected in the zeolite process. Care needed in the handling material. Careful handling is required because the material, that is lime and soda, both are corrosive in nature. Brine solution is required to be handled, which does not require much care. So this is something, the thing regarding the lime soda process and zeolite process. Now regarding the economy, process is economical and can be easily combined with the usual water treatment methods at a slightly higher cost. This process, because zeolite itself is costly, so this process is costlier. Hardness which can be treated. Excessively hard water, particularly those which are high in magnesium hardness, can be treated here in the lime soda process. Raw water with a hardness greater than 800 milligram per liter cannot be easily and economically treated here. That is for the zeolite process. Allowable turbidities in raw water. Highly turbid and acidic water can be treated here. Highly turbid water are difficult to be treated. In the ion exchange process, the turbid water you cannot use it because the suspended impurities deposited around the zeolite particles causes obstruction to the working of zeolite. Okay, so I think 12 points I have used to differentiate between the ion exchange process and the lime soda process. Now for the softening part, these two methods, lime soda process and the ion exchange method, both method concepts also we have discussed. One problem based on the softening part, that problem which I have discussed here, it is actually a 20-mark problem for a mains exam. But if you will solve this type of question, you will have a clarity about many concepts, and that is something which is required. That is something which is required. Okay. Okay. So in that case, now we can end this session for today. Thank you, everyone. We'll meet again on Monday. Same timing will be the same. Saturday, Sunday, we don't have a class. So again, we'll meet on Monday. For any information or for any discussion, this Telegram group is always available for you. Mrigank sir, PW. Clear? Any issue? Okay. So if nobody is having any issue, then we can end this session. Bye bye. Take care. We'll meet again in the next session. Till then, bye bye. Jai Hind.